All right, hello you guys. All right, so this is me, Mr. Arias. I'm going to be recording the lessons from now on, just for the next few days, because I won't be able to make it to class. And I'll be posting these on Canvas so you guys can look at them whenever you guys want to. You guys can look at them as many times as you want, however many times you guys want to, okay? So let's go ahead and let's get started with our lesson today. So our lesson for today on Monday is 7.2 volumes of solids with known cross sections. So now what we're going to be doing is we're going to be working with volume. Now before I get started on this lesson, I think it may be helpful if I showed you guys where this concept kind of comes from. If first we start with volume, which volume of a, let's say a sphere. Volume of a sphere is 4/3 pi r cubed. Now we already know that if we take the derivative of this, and we do this with respect to r, we're going to get dv dr, which is equal to 3 times 4/3 pi r squared. And so when that happens, this simplifies down to be 4 pi r squared. And then if we take the derivative one more time, so this is a derivative, if we take the derivative one more time of that, we would get 8 pi times r. Now the whole purpose behind this is this. The first equation up here at the very top, that's volume. When we took its derivative, the very first derivative, v prime of with respect to r, we found out that the equation that we got was 4 pi r squared, which in fact is actually equal to the surface area. And then when we took the derivative of surface area, you notice that we got 8 pi r, which I'm well aware that that's not actually circumference of a circle, right? Because circumference of a circle is 2 pi r, but this is 4 times that, right? So it's a constant times the circumference. Now, the whole purpose behind this is this. If we can take the derivative of volume and it gives us surface area, and if we take the derivative of surface area and we get a constant times the circumference, then what that tells us is that if we were to go backwards by integrating, that means that the integral of circumference of a constant times circumference would give us surface area, and then the integral of surface area would then give us volume. And so the main concept behind this, and the reason I brought this up, is you can see right here that the derivative of volume gives you surface area, ergo the integral of surface area should give us volume. And that ties into what we're talking about right here. If we want to find the volume with known cross sections, what do you have to do? You have to integrate the area. So right here it says for cross sections of area A of x taken perpendicular to the the x-axis, you're going to integrate with respect to dx. And I just want to go ahead and let you know that whenever you see this keyword right here, that they are perpendicular to the x-axis, that is your key, that everything is going to be with respect to x. So you're going to have a dx right here, and then your lower bound and your upper bound are going to be in terms of x. And then finally, what do you need inside? What we just talked about right now, you need the area of the object. So for example, if you take a look at this bottom right figure right here, this right here has area of a square. So if you wanted to do this one, you would do from A to B of the area of a square, which would be the area of a square is just side squared. So we would have some function in here, and suppose let's say this is with respect to dx. Though what would go inside of here would be the functions, which would be in this case top minus bottom. Okay, and I'm kind of running out of space here. Okay, and so that's kind of how that works. Now let's see one that's different. See this object right here? This one right here has shapes that are semicircles. So the area of a semicircle is pi r squared divided by 2. Now since pi over 2 is a constant, you can just leave this outside. And assuming this is with respect to dx, the x-axis, the rectangles are perpendicular to the x-axis. This will all be in respect to x. So you would have your lower boundary, x equals a, your upper boundary, x equals b. And then you need to integrate the area. So what's the area? Pi r squared divided by 2. Since I already have pi over 2 outside, I just need r squared inside. And of course, if this is with respect to x, you do top minus bottom. And if you're doing it with respect to y, remember that you do right minus left. Now let's go on to the next one. Now the next one is almost entirely exactly the same. The only difference you'll notice is that it says the cross sections are perpendicular to the y-axis. So when you see that, that's your key that this is dy. And again, it's pretty much the same thing. The lower bound will be y equals a all the way to y equals b. And then you need to integrate the area of whatever this shape may be. Now, there's an online website right here that you can use to play around with that may or may not show you three-dimensional shape of different figures. Now, by the way, it's not the only one. There are other websites if you want to go out there and just play around with it and just Google the area of cross-sections, calculus, etc., etc. There's other websites that'll do it for you so you can see what it looks like if you want to play around with it and get a visual aid. Now, on the next page, we already did that. Okay, so now let's go here. Now, for our next example, it says set up the integrals needed to find the volume of the solid whose base is the area bounded by these two lines and whose cross sections are perpendicular to the x-axis. So there's our key. Perpendicular to the x-axis, that means that we're going to integrate with respect to dx. There you go. There's our first part. Now notice it says right here at the beginning, it says set up the integrals. So you don't actually have to integrate. You just have to set up the integrals. So let's go ahead and let's do our graphs. Okay, so if we come over here, so y equals x squared is just a basic quadratic equation. And so 2, 3, 4, let's get this, that gives us this point. All right, there's a quadratic equation. Now let's get the linear equation, negative 2x plus 3, which is a y-intercept of 3, slope of negative 2. So this should look like this. And there is the area bounded by the two shapes right here. Now, we have to be able to set up the integral. So in part A, I know there's a typo right here. It should just say rectangles of height 4. So first, let's start off by doing this. What's the area of the rectangle? Well, an area of a rectangle is base times height. And they're already telling you that the height is 4. So that's 4 times the base. Now, all we have to do now is translate that into the integral. Well, since 4 is a constant, we can just leave that outside. So I'm just going to go ahead and just leave that right out there. Now, we already found out that this is with respect to dx, so that's going to go here. Now, the next thing we need to find are what the boundaries are of this shaded area. So to find the 2 points, right, the upper and lower bound is we're going to make both of these lines equal to each other. So x squared equals this. And if we just work a little bit of algebra in here, we should get this. And there's our lower bound and upper bound. So from negative 3 to 1. So there they are. And now the last part is we need to find what the base is. Well, the base is this shaded area we have right here. Now remember, use the content that we talked about when we were finding the area between two different functions. Whenever it's with respect to dx, remember that we still have to do top minus bottom. So this really hasn't changed. You're still going to do top minus bottom. So what's the top function right here? The top function is negative 2x plus 3. So negative 2x plus 3 minus, and what's the bottom function? The bottom function is x squared. And so there's the base, b. 4 is the height. There it is. There's your limits, the lower and the upper bound. And there you go. This will give you the volume with rectangles. Now, if you're wondering, if you're curious and you want another visual aid of what this is looking like, okay, here. I'm going to go back here, erase this, and let's see if we can get some shapes in here. All right, here's a rectangle. All right, let's see if this will work correctly. All right, here's a rectangle. Assume this is a height of 4. So there's one rectangle. Here's another one. And basically, when you integrate, it does this process forever. If you remember from Riemann sums, remember that a Riemann sum, an integral, is infinitely many rectangles. Well, in this case, what's happening is that you're getting these rectangles, but they're coming out of the page into three-dimensional space. So that's kind of the newer version where we're going to, the new direction we're taking, is that now instead of finding area, we're finding volume. All right, now let's go to the next one. In part B, it says that the cross sections are semicircles, which is kind of like this shape that we just did a second ago. It's kind of like this one, where they're semicircles. So you're going to get those kinds of shapes. So if we go back over here, now we don't really have to do much because it's the same exact equations, same boundaries. Essentially everything is really the same, so we can kind of just copy and paste these boundaries right here, just put those in there. It's still going to be top minus bottom, so we can go ahead and fill this in. And it's still with respect to x. There's that part. Now the only other part we're missing is that they're semicircles. Now we already talked about this. A semicircle is really pi r squared. The area of a semicircle is pi r squared divided by 2. And so pi over 2 I will leave outside. And r squared is represented by this distance right here. So all you have to do is put a little square. And there you go. You are finished. Okay. All right, and that will give you the volume with semicircles coming out of them. Now let's go ahead and let's go to our next example right here. So right here it says, set up the integral needed to find the volume of the solid whose base is the area bounded by the circle, x squared plus y squared equals 9, whose cross sections are perpendicular to the x-axis. Again, that's one of our context clues. And it also says the cross sections are equilateral triangles. Now let's go ahead and start setting up some of the basics. So some of the basics I'll set up is, first I want to put my integral. It says the cross sections are perpendicular to the x-axis. I'm going to put a dx in here. Now fortunately they gave you the area of an equilateral triangle. So the area is root 3 over 4. So I'm going to go ahead and just plug that in. Now we don't exactly know what the side of the equilateral triangle is just yet, so I'm just going to put that in parentheses and put the square outside. So now all we really have to do now is find the boundaries and then find out what goes inside of this parenthesis squared. Now x squared plus y squared equals 9 is a circle with radius 3. So that, let's go ahead and fill that in. And you should get, well, my circle's not exactly perfect. I guess here, let's try it again. There you go. There's a circle. Now, there is one slight little tricky thing about this. We need an equation that's in terms of x. So we need y equals something. Well, if you solve for y, that equation would be 9 minus x squared, and then you take the square root. Now, if you recall, you remember that that equation will only give you the top half. It'll only give you what's above the x-axis. We need the bottom part. Well, the bottom part is going to be the same equation but with a negative right in front. And so that's the bottom equation. So to figure this out, to do top minus bottom, it's really just the square root of 9 minus x squared minus a negative square root of 9 minus x squared. And that looks just a tiny little bit messy, so let's just clean this up. So this is root 3 over 4. Now, by the way, these two negatives will cancel out, so you'll get just two of them. So 9 minus x squared squared dx. Now, we're just missing the boundaries. Now, if you come over here and you look right here, the boundaries in terms of x is going to be from negative 3 all the way to 3. So from negative 3 to 3. Now, of course, yes, I'm well aware that 2 squared is 4, and the square root and the square cancel out, but that's just mere algebra. Now, if we do that, we can just simplify this. 2 squared will give us 4. I'll move that outside. I'll put my boundaries back up here, and we're left with this. And, of course, these 4's cancel. Now, it said right here, set up the integral needed. Do not actually solve. Now we're going to stop right here because that actually does give us the integral of the volume, right? We're not going to solve it because, well, at this level, we know how to integrate that. Okay, so now let's go on to our next question. Now this one's slightly different because if you notice, it says the cross sections are perpendicular to the y-axis, and it says that the shapes are squares. So remember, we're going to integrate, because it says perpendicular to the y-axis, is dy. Now remember that we need to integrate area in order to get volume. So what's the area of a square? Area of a square is just side squared. So I'm just going to put my little parentheses, my square, because this right here, essentially, this represents the side of the square. And we're going to get that from the two functions that we're about to graph right now. Now, let's go ahead and let's graph it. Again, we have a basic quadratic equation, which is going to look like this. So here's our quadratic equation. Then it says that one of the boundaries is y equals 0, so that will be this, y equals 0. And then the other one is x equals 2, so that'll be here, and there it is. Okay, so there it is, x equals 2. Now let's go ahead and set up the integral. Now you notice it's with respect to y, so remember that when you do with respect to y, we need to do right minus left. So if you look at your graph right here, which function is the farthest right? The one that is the farthest right is this vertical line of x equals 2. This is the farthest rightmost function. So that'll just be 2 minus. Now we need the function that's to the left. To the left is this quadratic equation. But if you remember, this is in y equals form. We need something that is x equals. So this will just be nothing more than just x equals root y. So that is the function that's on the left. So we plug that in. Okay, that gives us the side of the squares. Now we're just missing the boundaries. Now remember, since this is with respect to y, we need the boundaries with respect to y also. So the lower limit is 0, if you look at your graph right here. And the upper bound, well, we would make these equal to each other. So if you do that, we get root y is equal to 2. We square both sides and we get y equals 4. And so the upper bound right here is y equals 4. And there you go. This will give you the volume with cross sections that are squares. And again, if you wanted a visual aid, now the only difference between this one and the other ones that I drew earlier is that because this is with respect to y, dy, the widths of the squares are going to be like this. They're going to be going towards the y-axis, making, I guess, a 90-degree angle with the y-axis. And so you get these squares that come out of the page like this. And so, like this, you get these squares. Okay? Now, that concludes this lesson. So this is the lesson for Monday. So if you guys want to keep looking at this and review it over and over again, well, by all means, go ahead and use it. So this will be a lesson for Monday. Please follow your calendars. Everything will go basically according to plan. The only real difference is that it says you have a quiz scheduled for Wednesday. Instead, the quiz will be moved to Friday because it has area, volume of cross sections, and it also has disk and I believe washer method. So the quiz will be moved to Friday, but today's lesson and homework will be the same. The lesson and homework for tomorrow, which is this, is still going to be the same. So make sure you follow your homework and you keep up with it. Now, let's go ahead and let's start on Tuesday's lesson. This is Tuesday's lesson. If you want to go ahead and stop right now, you can go ahead and stop right now because I'm going to start Tuesday's lesson. And you can just review the first part as much as you want. Now, if you want to go ahead and get ahead, then by all means, you can watch this lesson. You can watch 2 lessons in 1. That's fine with me. So this resource is here to help you. All right, so let's go ahead and let's get started. So day 2, 7172 area and volume of cross sections. First example, it says let R be the region bounded by the graphs of 3x and x squared. So again, we have some quadratic equation. Here we go. It's going to look like this, and there's the equation. And 3x has a slope of 3, so that's 1, 2, 3 over 1. And so we get a graph that looks like this. Now, please forgive my drawings are not perfect. Okay. So this right here is our shaded area. So it says draw a figure and shade the area, shade the bounded region. Then find the area of R. Okay, so now we actually do have to find the area of R. So let's go ahead and let's start with our basics. So I'm going to integrate. Now here's a key right here. Notice it did not say with respect to X or Y. So you're actually free to find the area of this any way you feel like it. Now remember, if you remember from the week before spring break's lesson, that you actually do get the same exact area regardless of whichever way you choose to do it, okay? Now just for conventional means, because it's already in y equals, I'm just going to go ahead and just do it with respect to x. So let's go ahead and let's do it. Since I'm doing it with respect to x, remember that you do top minus bottom. So what's on top? In this shaded region, it's that linear equation right there, which is 3x. Then I'm going to subtract the bottom equation. So the bottom is going to be this square root function, y equals x squared. So that'll be this. And now we need to find the boundaries. So we make these equal to each other. And we're going to get this. And with a little bit of algebra, we find out that the limits are going to be 0 and 3, which one of them was easily visible from the graph. So there it is. Of course, if you want to verify, you can always plug 3 into both of them. You'll see you'll get 9. So now let's go ahead and let's integrate. If you integrate this, you're going to get 3x squared over 2 minus x to the third over 3, evaluated from 0 to 3. And so let's go ahead and let's substitute in our values. So we get 3 halves times 3 squared is 9 minus 3 to the third over 3 minus, I'm just going to put a big 0 right here because when you substitute in the lower limit, you get 0. And so 3 times 9 is 27 over 2. Here, I'm going to use a property of exponents. This 3 cancels out one of these 3's, so 3 squared is 9. And then if I get common denominators, this is going to be 27 minus 18 over 2, which is then 9 halves. And by the way, like I said, if you want to check your work in practice, doing it with respect to y, by all means go ahead and try, and then you can come back here, watch the video, and check your answer again. You should get the same exact area. You should still get 9 halves, even if you make an integral with respect to y. Just remember, the equations have to be in terms of y, and remember you do right minus left. So now let's go ahead and let's do part B. Now in B it says the region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis, so that right there already tells me one part, that I need a dx in here. Then it says is an equilateral triangle. Now from the previous lesson, you remember that the area of an equilateral triangle is root 3 over 4 times s squared. So I'm going to put my constant outside, and the side squared goes inside. It says write but do not evaluate an integral expression that gives the volume of the solid. Now this is going to be identically the same in terms of limits. So what were the limits before? 0 and 3. So you plug in 0 and 3, that goes there. Now you're still going to have the same thing. When you do with respect to x, remember you still do top minus bottom. So what was the top function? 3x. What was the bottom function? Minus x squared. And so it says write but do not evaluate. So there you go. Okay? All right, and there you go. That's it. Now let's try part C. It says the region R is the base of a solid. For this solid, each cross-section perpendicular to the y-axis is a square. So let's go ahead and use that information to start filling in our integral. So that's an integral with respect to y, and it says that they are squares. So the area of a square, again, the area of a square is side squared, so you're just going to put a parentheses in here and square. Okay. By the way, I would make a good habit. I know that I would make a habit of putting parentheses because when we do disk and washer method, it'll help keep things in order in your integrals. Now it says write but do not evaluate an integral expression that gives the volume of the solid. Now it says it's with respect to y, so I need the functions with respect to y. I have the area of a square, so that's squared. Now I need the limits. So since we're still doing the same problem, let's go back up here. Now what are the limits in terms of y? Not in terms of x this time, but in terms of y. Well, this lower bound right here is y equals 0. Now the upper bound, which is going to be right here in this region right here, what happens when we plug in 3 for both of these equations? If you plug in 3, you get 9 for both. So that means our boundaries are 0 to 9. So here we go. Here's our boundaries, 0 to 9. Now the last thing I need to do is to put the equations inside. Now remember, this is dy. This is with respect to the y-axis, so we do right minus left. So let's go back up here. What equations do we have? We have y equals 3x and y equals x squared. So let's get each one in terms of y. All right, there they are. Okay, which one is the one that is the farthest most right function? So you always use your graph as visual aid. So which one is the farthest most right function? So I'm going to go back over here. I'm going to erase this. So here, let's get this out of the way. Okay, this time the quadratic equation, this one right here, is the one that is the farthest to the right. So that one's going to go first, which is y equals x squared, which is now the square root of y. So square root of y minus the other one, which is y over 3. And so there you go. And it says right, but do not evaluate. And so there it is. Now let's see what else we got. Oh, you guys are supposed to have a ticket out, but again, since I'm not going to be in class, we're not going to do this. All right, you'll have plenty of homework for this part. Okay. Now, all right, so just a couple of just comments. All right, so you notice that on some of these we're just writing the integral and we're not actually finding the volume. All right, you actually are going to be required to do that on your quizzes and tests, and also on the AP exam they do that sometimes, where they just ask you to just write the integral that gives volume, and that's it. All right, so by the way, I have mentioned in the past, but I'm just going to go ahead and just touch on it again. Now more than ever, this part right here, the d, dy, dx, this is very important. All right, so if you're one of those people and you're forgetting to write that down, okay, you're going to start losing more than 1 point this time. All right, it's very important that this dimension matches whatever's inside the integral. These two need to match, by the way, just in case you're not aware of that. And so part of what you guys are going to have to be able to do is just write the integral that gives volume, okay? All right. And so as I mentioned before, your quiz will be on Friday. That concludes Tuesday's lesson. All right. So good luck. Use it as much as you'd like. By the way, if you know someone who's not able to look at the videos or lessons, I guess email me. I'm going to try to do my best to make sure that everyone can view these. Okay? All right. Well, good luck, you guys.